A single pencil stroke on a blank page could one day become our first starship. Carl Sagan once reflected that the cosmos is within us, that we are made of star stuff. This is the profound journey we are embarking on, the transformation of pure imagination into interstellar reality. The artistry behind unseen propulsion systems stands as one of humanity's most ambitious creative and technological frontiers. How does a fleeting sketch evolve into a vehicle capable of crossing light years? By the end of this exploration, you will understand the complete creative engineering process that turns abstract concepts into cosmic vessels. We will travel from the first concept drawings through the complex world of theoretical physics and beyond. What invisible forces must be mastered to sail between the stars? That initial pencil stroke is often born from a single, silent question in a curious mind. Long before engineers calculate stresses or physicists model fields, artists and visionaries dare to sketch the impossible. This is the genesis of every great interstellar concept, a place where rigid scientific problems collide with unbounded creative intuition. Consider the notebooks of Leonardo da Vinci, filled with intricate designs for flying machines and helical helicopters. In his era, the physics of flight were a complete mystery, yet his imagination soared centuries ahead of the technology required to build them. His sketches were not mere fantasy. They were detailed thought experiments, a process of working out complex ideas through visual means. This tradition of speculative thinking is the very cradle of revolutionary propulsion. Theoretical physicist Michio Kaku often emphasizes that to solve the grandest challenges, we must first give ourselves permission to think far beyond the boundaries of our current labs and tools. This is how we stretch the fabric of the possible. The first tangible form of a warp drive or an antimatter engine is not a metal prototype. It is a diagram, a few curves on a page that give shape to an equation. The now famous Alcubierre drive, for instance, began as a mathematical solution to Einstein's field equations, but before it could be debated in journals, it needed a simple schematic. A basic drawing of a spacecraft nestled within a warp bubble, compressing spacetime ahead and expanding it behind, transformed an abstract tensor calculation into a visually compelling idea that the entire scientific community could grasp and explore. These initial sketches and digital models are far more than simple illustrations. They are the foundational blueprints for innovation, translating a physicist's complex formulae into a shared vision that engineers can eventually strive to build. So what does this mean for the ideas taking shape today? A student doodling in a margin, a researcher's late-night diagram on a whiteboard, these are the seeds. Which of these nascent concepts, born from a moment of pure imagination, will one day be refined, tested, and forged into the vessel that carries humanity to another star? Sid Mead, the legendary visual futurist, never saw a boundary between art and engineering. His iconic designs for films like Blade Runner and Tron did more than just define the look of the future. They gave engineers a tangible goal to reach for. His sleek vehicles and sprawling cityscapes were not just beautiful, they were believable. They felt like they could work, and that believability is the artist's most crucial contribution to interstellar design. Artists like Mead act as essential translators, taking the raw, often impenetrable language of theoretical physics and turning it into a visual narrative that everyone, from a materials scientist to a funding committee, can understand and rally behind. This is a profound partnership. The artist asks, what would a warp bubble actually look like as it distorts the starlight around it? How might the vast, gossamer thin sail of a light-sail spacecraft be depicted to convey both its incredible fragility and its immense strength? Their answers are not mere decoration. They are thought experiments rendered in light and shadow. A concept artist working with a space agency today faces a unique challenge: aesthetic functionality. Every curve on their digital model must serve a purpose beyond visual appeal. The sweeping lines of a hull are not just dramatic, they are calculated to minimize the impact of microscopic interstellar debris at a fraction of light speed. The choice of a white or mirrored surface for a spacecraft is not arbitrary. It is an application of color theory for managing extreme heat from nearby stars or for passive thermal regulation in the deep freeze of space. These artistic decisions are foundational to the engineering process. When the public sees a stunning rendering of a ship riding a solar sail, they are not just looking at a pretty picture. They are seeing a complex physics principle made accessible. The billowing sail captures sunlight not as rays, but as tangible particles of light, each imparting a tiny push. This visualization helps secure the cultural and financial support needed to turn the concept into a blueprint. One contemporary artist put it perfectly, saying their job is to build the dream so clearly that the engineers can then build the reality. This synergy is where true innovation ignites. The artist provides the compelling vision of the destination, while the engineer charts the practical course to get there. They are not two separate disciplines moving on parallel tracks, but a single, intertwined force pulling the future into the present. So the next time you admire a piece of spaceship concept art, look closer. See the engineering solutions woven into its form and ask yourself, is this the vessel that will one day carry us to the stars? This bridge between imagination and physics is a structure built over a chasm of impossibility. On one side lies the cliff of pure creative vision, and on the other, the solid ground of physical reality. Connecting them requires the work of theoretical physicists, the master architects who take an artist's beautiful sketch and ask a single, brutal question: but will it hold under the weight of the universe's laws? They are the ones who test these dreams against the unyielding mathematics of general relativity and quantum mechanics. A concept for a wormhole, depicted as a magnificent tunnel through folded space, must first be a stable solution in a set of field equations. The thrilling promise of antimatter propulsion, with its perfect matter-energy conversion, hinges entirely on our ability to produce and contain infinitesimal amounts of this volatile substance without it annihilating upon contact with everything. The physicist Kip Thorne often spoke of this need for mathematical elegance, a kind of inherent beauty and simplicity in the equations that suggests a concept is not just possible, but perhaps even probable within the grand scheme of the cosmos. This validation process is anything but a single step. It is a relentless, iterative loop where the initial sketch is constantly modified. An artist's rendering of a warp drive might show a sleek, centralized hull, but the physicist's computational model may reveal that the energy requirements demand a vast, ring-like structure to generate the necessary spacetime distortion. The sketch is then revised, the model is run again, and the design evolves in this dance between aesthetic vision and computational truth. Consider the controversial case of the M drive. Initial reports described a revolutionary engine that could generate thrust without propellant, a concept that immediately captured the public's imagination and spawned countless artistic interpretations. Yet when subjected to rigorous scientific scrutiny, the results could not be consistently replicated, and the proposed mechanism conflicted with fundamental conservation laws. The excitement was ultimately tempered by physics, a necessary but often disappointing part of the process. This constant confrontation with reality forces us to look at our own understanding of these laws. Are the physics we hold as absolute today the final word, or merely a close approximation of a deeper truth waiting to be discovered? Could a future reinterpretation of quantum gravity or dark energy suddenly validate a sketch that currently sits in the realm of fantasy, transforming it into the blueprint for tomorrow's interstellar vehicle? A hot tungsten nozzle takes shape inside a vacuum chamber, built not by human hands but by a laser fusing metal powder one precise layer at a time. This is the moment the ethereal becomes tangible, where a propulsion concept is forged into a physical component you could hold in your hand. That ion thruster, materializing from a digital blueprint, makes an invisible force visible. Its intricate grids and electrodes are designed to channel a stream of charged particles, creating a gentle but continuous push. This is the frontier of advanced materials science, the discipline that must answer a monumental question. What substances can we possibly create that will not vaporize, shatter, or decay under the unimaginable stresses of interstellar travel? The answer lies in the laboratory synthesis of new forms of matter. To contain a theoretical warp bubble, physicists speak of metamaterials, substances engineered with properties not found in nature. Imagine a composite lattice so finely structured it could manipulate gravitational waves or spacetime itself, serving as a stable casing for the universe's most fundamental fabric. For light sail structures, the miracle material is graphene, a sheet of carbon just one atom thick yet stronger than diamond. Projects like Breakthrough Starship rely on such nanomaterials, envisioning sails that are simultaneously ultra-light, highly reflective, and incredibly resilient. A materials scientist at NASA, a jet propulsion laboratory, once described their work as creating matter for unseen forces. They are not just selecting from a catalog of existing metals and ceramics. They are digitally designing and then growing entirely new molecular architectures from the atom up. Consider the phenomenon of quantum locking, where a superconductor is cooled to extreme temperatures and levitates perfectly stable over a magnetic track. This isn't just a laboratory curiosity. It is a principle that could be harnessed for propulsion stability, allowing a spacecraft to maintain a perfectly aligned position without any moving parts or active power. Every gram saved in a spacecraft's mass translates directly into greater speed and range, a tyranny of the rocket equation that makes the pursuit of nanomaterials for energy efficiency absolutely critical. But how do we test these fantastical materials against the brutal realities of deep space? We cannot simply build a full-scale prototype and hope for the best. The process demands a different kind of forge, one that exists not in the physical world, but within the silent, lightning-fast circuits of a supercomputer. A designer slips on a virtual reality headset and suddenly stands inside the heart of their own creation, a full-scale model of a fusion-powered spacecraft. With a gesture, they reach out and adjust the alignment of a magnetic confinement coil, watching as the system's digital aura of simulated plasma flow instantly stabilizes. This is the digital canvas where the hand-drawn sketch transforms into a living, breathing prototype long before a single piece of metal is ever cut. The tools enabling this revolution are computer-aided design, or CAD, and computational fluid dynamics, or CFD. CAD software builds the precise digital skeleton of the vehicle, while CFD acts as a virtual wind tunnel, simulating how exotic forms of propulsion would interact with the fabric of spacetime itself. Artists and engineers can now input the theoretical principles for a drive that harnesses something like the Casimir effect, the subtle quantum pressure of empty space, and the software will generate a visualization of the energy flows and the immense structural stresses that would result. It turns abstract equations into a dynamic, visual performance. Software developers at companies like SpaceX describe building digital twins, perfect virtual replicas of spacecraft that exist entirely in code. The process often begins with scanning an initial hand-drawn sketch, its organic lines translated into a wireframe model. From there, parametric design principles take over, allowing every component to be adaptive. Change a single variable, like the desired maximum velocity, and the entire model intelligently reconfigure its geometry, shifting the size of a thruster bell or the angle of a stabilizing fin to meet the new performance target. NASA's development of the Orion spacecraft provides a powerful case study in this digital artistry. Using sophisticated software platforms like Siemens NX, teams created and tested countless digital iterations of the crew module, running it through thousands of simulated re-entries to find the perfect balance of heat shield shape and aerodynamic stability. This digital forge allows for a kind of accelerated evolution, where only the most resilient and efficient designs survive to be considered for physical manufacture. This entire process raises a profound question about the future of creativity itself. If software can already simulate and refine our most ambitious ideas, what happens when artificial intelligence begins to generate its own propulsion designs? We are approaching a frontier where the initial spark of an idea may not come from a human mind at all, but from an algorithm that has learned the fundamental laws of physics and can dream within their constraints. An orchestra does not create a symphony with a single violin. In the same way, a starship's journey relies on the perfect harmony of its many systems. The main propulsion drive might be the powerful cello section, but it is useless without the violins of navigation, the percussion of power generation, and the woodwinds of life support, all playing from the same sheet of music. This discipline of orchestration is called systems engineering, and its practitioners are the conductors who ensure the artist's original vision survives contact with brutal functional necessities. A systems architect at a major aerospace firm describes their role not as a designer of parts, but as a negotiator between conflicting demands. The beautiful, sweeping hull from the concept art must now accommodate the mass of a fusion reactor, the volume of radiation shielding, and the intricate plumbing for attitude control thrusters. These tiny thrusters, often using simple cold gas or ion emission, are the unsung heroes of interstellar travel. While the main drive provides the tremendous push for acceleration, these smaller systems are responsible for the delicate ballet of course corrections, ship rotation, and most critically, the final braking maneuver at the destination star. Without them, a vessel would fly past its target at a significant fraction of light speed, a truly tragic end to a millennia-long journey. This integration demands constant compromise. Every component added to ensure reliability through redundancy, like a backup power bus or a duplicate computer core, adds precious mass. Every module designed for future upgrades, allowing a new type of sensor or thruster to be swapped in decades into the mission, introduces complexity. The systems engineer's art is to balance this mass, energy, and complexity without breaking the elegant proportions that made the original sketch so compelling. Consider the fictional USS Enterprise from Star Trek. Its iconic saucer section, engineering hull, and nacelles are not just aesthetically pleasing shapes. They represent a logical segregation of functions, implying a design where the warp drive in the nacelles is isolated from the primary crew areas in the saucer, while the deflector dish at the front seamlessly integrates with both propulsion and navigation to clear a path through interstellar dust. This fictional design succeeds because it feels integrated, a single organism rather than a collection of bolted-on parts. Managing such profound complexity is the ultimate challenge. How do you ensure that a vehicle intended to operate flawlessly for centuries with no chance for roadside repairs remains as elegant as the first pencil stroke that conceived it? The answer lies in viewing the entire Starship not as a machine, but as a single, living system where every component, from the mightiest engine to the smallest microchip, breathes in unison toward a common goal. A miniature antimatter containment vessel, a concept once confined to whiteboards and physics papers, now rests in the palm of a student's hand. At a university lab, a team recently translated a theoretical magnetic bottle design into a tangible object using a high-resolution 3D printer. The plastic model is inert, of course, but its physical presence changes everything. Engineers can now run their fingers over its complex electromagnetic coil geometries, feeling for potential assembly conflicts that a flat screen could never reveal. This is the power of prototyping the impossible, turning ethereal ideas into objects you can literally hold, rotate, and question. Rapid prototyping technologies like additive manufacturing, commonly known as 3D printing, and interactive holographic displays are revolutionizing this phase. They allow teams to iterate on a propulsion system's physical form in days or even hours, compressing a development cycle that once took years. A prototype engineer at Blue Origin once noted that the moment a design becomes a physical object, it starts talking back to you. It points out its own flaws, its awkward angles, and its hidden assembly nightmares long before any costly metal is ever cast. These models are not built for flight. Their purpose is profoundly human. They test ergonomics for maintenance crews, validate the step-by-step logic of assembly procedures, and become powerful tools for public engagement, making the unimaginable feel imminent. The process demands careful selection of materials to achieve the right fidelity. A model meant for a wind tunnel test might be printed in a rigid polymer to withstand aerodynamic forces, while a display model for a museum might use transparent resin to showcase its intricate internal latticework. These prototypes then face simulated environments, from supersonic wind tunnels that mimic atmospheric entry to vacuum chambers that test component behavior in space-like conditions. Consider the meticulously detailed mock-up of the Hermes spacecraft from the film The Martian. While a fictional vessel, its fully realized interior and exterior sparked genuine engineering discussions about long-duration crew habitats and vehicle layout efficiency. It served as a functional prototype for a conversation, proving that a compelling physical model can bridge the gap between science fiction and science fact. So where do we draw the line? When does a beautifully crafted model of a warp drive nacelle stop being a functional prototype and become a piece of artistic sculpture? Perhaps the most profound prototypes live in both worlds, serving as both a tool for solving technical problems and a sculpture that embodies the sheer audacity of our interstellar dreams. The nozzle of an ion engine is a sculpture carved by physics itself, its graceful bell shape not an artistic flourish but a precise conduit for energized plasma. Every contour is mathematically optimized to accelerate charged particles to tremendous speeds, minimizing turbulence and maximizing thrust from every precious watt of power. This is the profound truth of interstellar vehicle design, where aesthetics are not about decoration but about survival. The principle that form must follow function becomes the absolute law when your journey spans light years and every gram of fuel is irreplaceable. The color of a heat shield is never an arbitrary choice. A white or mirrored surface reflects intense stellar radiation, passively cooling the vessel, while a black coating might be strategically applied to areas that need to absorb heat for thermal regulation. Surface texture, too, plays a critical role. A microscopically rough finish on a radiator panel can dramatically increase its surface area, allowing it to dump waste heat into the void more efficiently. a simple geometric trick that can mean the difference between a functional ship and a melting one. Industrial designers working in aerospace operate at this fascinating intersection. They speak of a necessary balance between sleek visuals and the brutal demands of thermodynamics. A beautifully streamlined hull isn't just pleasing to the eye, it's aerodynamically stable if the ship must ever enter an atmosphere, and its smooth surface presents fewer points of stress where micrometeoroids could cause damage. This philosophy often draws inspiration from the natural world through biomimicry. The structure of a bird's hollow bone, incredibly strong yet lightweight, inspires the internal bracing of a spacecraft's fuel tank. The fractal branching pattern of a leaf's veins, so efficient at transporting fluids, is being studied to design coolant channels that maximize heat transfer with minimal pumping power. Look at the SpaceX Raptor engine, a masterpiece of visible complexity. Its intricate weave of piping and stark, metallic form is not just for show. Each line is a carefully routed path for cryogenic fuel, and the engine's compact, powerful appearance is a direct reflection of its immense performance. This visual communication is vital, building public trust and demonstrating engineering confidence. Yet these efficient forms must also be safe for the crews who trust their lives to them. Sharp, exposed edges are not only inefficient for airflow but pose a danger during extravehicular activity. The psychological comfort of a crew on a multi-generational voyage may one day depend on the harmonious, calming lines of their environment, proving that efficiency encompasses human factors as well as physical ones. How do we ensure that a vessel designed for such brutal performance remains a sanctuary for the fragile humans inside? A spacecraft enters a wormhole, and for a few simulated seconds, every sensor reading goes insane. The fabric of spacetime itself twists in ways our physics cannot yet describe. This is the ultimate design challenge, engineering a vehicle for environments and forces that lie entirely beyond the boundaries of human experience. We are not just building for the vacuum of space anymore. We are building for the possibility of temporal distortions, for the mind-bending geometry of higher dimensional spaces, and for encounters with exotic matter that behaves unlike anything in our periodic table. How do you design a navigation system when the stars outside your window might not be where or when they appear to be? The cosmologist Lisa Randall, who explores the potential realities of extra dimensions, suggests that our universe may be a three-dimensional membrane floating within a higher dimensional bulk. A propulsion system capable of moving through such a reality would not merely push against space. It would need to navigate it, perhaps by manipulating those very dimensions to create shortcuts. Artists and physicists collaborate on this problem by turning to abstract art and speculative models. They create visualizations of higher dimensional objects projected into three dimensions, strange, twisting shapes that help engineers conceptualize the stresses such geometries might impose on a ship's hull. These are not just pretty pictures, they are essential tools for brainstorming safety protocols. What kind of structural integrity could withstand forces that operate in more than three spatial dimensions? The answer lies in designing for profound redundancy and adaptability. Navigation cannot rely on a single star-fixing system. It must layer pulsar-based timing with inertial guidance and a form of gravitational wave sensing, all cross-referenced to identify any discrepancies caused by spacetime warps. Material scientists are theorizing adaptive coatings, surfaces embedded with nanoscale processors that could change their fundamental properties in response to unknown stresses, shifting from a reflective state to an energy-absorbing one in milliseconds. Every power conduit and energy containment unit needs fail-safe mechanisms that assume the energy source itself could become unpredictable. Consider the incredible legacy of the Voyager probes. They were engineered with a degree of robustness for the unknowns of the outer solar system, built with redundant systems and programmable flexibility. No one knew for certain what they would find, yet they have sailed far beyond their intended missions, a testament to designing for resilience in the face of the unknown. Their success makes you wonder what other invisible thresholds might an interstellar vehicle cross. What whispers of forces do we not yet have instruments to hear? Our designs must become like a living organism, capable of sensing, adapting, and enduring realities we can currently only sketch on the very edges of our understanding. The iconic silhouette of the Starship Enterprise, with its glowing warp nacelles, is more than a cultural landmark. For generations of physicists and engineers, it was a direct challenge, a visual question that demanded a scientific answer. How could we make that beautiful idea real? This is the profound role of science fiction, a laboratory of the imagination where propulsion concepts can be explored without the constraints of our current technology or budget sheets. In this boundless creative space, authors and artists construct entire narratives around theoretical drives, providing a complete framework that real-world scientists can then dissect for feasibility. Frank Herbert's Dune, for instance, hinges on the Holtzman engine, a device that folds space. While purely fictional, the concept forces a conversation about the nature of spacetime itself and what manipulating it would truly entail. Similarly, the Epstein drive from The Expanse offers a brutally efficient fusion engine, its realism grounded in known physics, which has sparked serious discussion among aerospace engineers about high-G travel and the human body's limits. Author Andy Weir, in crafting the Hermes spacecraft for The Martian, famously prioritized accuracy, consulting with NASA to ensure every burn and trajectory was not just compelling storytelling, but a plausible depiction of near-future propulsion. This creates a powerful feedback loop. A speculative idea from a novel or film is presented at an aerospace conference where engineers analyze its underlying assumptions. Their critiques and insights then filter back to a new generation of science fiction creators who incorporate this sharper understanding into even more grounded and inspiring designs. Consider the moment astronomers discovered the TRAPPIST-1 system, a real-life solar system with multiple Earth-sized worlds orbiting a red dwarf star. It felt like science fiction made manifest, a scenario depicted in countless stories suddenly becoming a tangible scientific target. This cycle of inspiration and analysis begs a personal question. What fictional vessel captured your imagination first? The sleek fighter from your favorite anime, the rugged freighter from a beloved series, the generation ship from a classic novel? That initial spark of wonder is not trivial. It is the very same creative impulse that fuels the researchers and artists who are, right now, sketching the blueprints for our interstellar future. Your favorite fictional ship might just contain the seed of the next great propulsion breakthrough. Ancient myths of Vedic Vimanas and sun chariots share a stunningly similar goal with modern blueprints for fusion rockets, a deep human urge to break free from the ground beneath our feet. Across cultures and millennia, the artistry of propulsion has always been a mirror, reflecting the values, fears, and aesthetic ideals of the society that conceived it. The sleek, streamlined forms of early 20th century rockets did not emerge from a vacuum. They were born from the Art Deco movement, with its celebration of speed, industry, and machine-age aesthetics. These vessels looked like they belonged in a world of skyscrapers and luxury liners, their fins and chrome surfaces speaking a visual language of optimistic progress. Contrast this with the minimalist, almost biological curves favored in many contemporary designs, which echo our current cultural shift towards clean energy, seamless digital integration, and biomimicry. A historian of technology might note that you can read a nation's ambitions in the silhouette of its spacecraft. The brutalist, formidable look of the Soviet Buran shuttle, for instance, was not just an answer to the American space shuttle. It was a physical manifestation of a different political ideology and engineering philosophy, emphasizing raw power and functional austerity. This cultural imprint extends to the smallest details. The incredible precision of Japanese rocket components reflects a centuries-old tradition of master craftsmanship and an aesthetic pursuit of perfection. The vast, cathedral-like truss structures proposed for some interstellar arcs subtly echo the grandeur and upward aspiration of European Gothic architecture, framing the Starship as both a vessel and a monument. The great space race of the mid-20th century acted as a massive catalyst, funneling unprecedented resources and global attention toward these artistic endeavors. Suddenly, the dream of propulsion was not just a sketch in a notebook. It was a national priority, with teams of artists and engineers working to give a face to humanity's cosmic ambitions. So what does our own global culture value today as we stand on the cusp of a new age of exploration? Is it sustainability, collaboration, or perhaps a new form of digital consciousness? However we answer, those values will be forged into the hull and engines of the next generation of starships, destined to carry our cultural signature far into the cosmos. A propulsion system powerful enough to reach the stars carries with it an immense moral weight, one that falls squarely on the shoulders of the artists who envision it and the engineers who build it. Picture the moment a vessel arrives at a world orbiting another sun, a world that may hold its own fragile, nascent life. The simple act of landing, of a single microbe escaping from a vent port, could irrevocably alter or erase an entire alien biosphere. This is the profound responsibility of planetary protection, a principle that forces designers to treat every component as a potential vector for contamination. Ethicists working with space agencies argue that our first interstellar probes must be sterile, not just clean, requiring propulsion systems and hull materials that can withstand the most extreme decontamination processes without compromising their function. The ethical questions multiply from there. Who has the right to build and launch such a vehicle? If the technology for interstellar travel is phenomenally expensive, does it become the exclusive domain of a handful of powerful nations or corporations, creating a cosmic divide between those who can leave Earth and those who are left behind? The design process itself must actively include diverse global perspectives to avoid embedding a single culture's biases into the very architecture of the Starship, ensuring it represents all of humanity, not just a privileged part of it. This ethical framework directly shapes the blueprints. It pushes teams towards propulsion methods with minimal long-term pollution, even in the vastness of space. The controversial history of nuclear propulsion serves as a powerful case study. The idea of using miniature atomic explosions or fission fragments for thrust offers incredible power, but it also raises the specter of a launch failure dispersing radioactive material into Earth's atmosphere, or a spacecraft accident turning a pristine alien moon into a nuclear waste site. Ethical engineering demands not just that such a system works, but that it includes multiple, redundant fail-safes to contain its hazard under any conceivable failure mode, from a computer glitch to a high-speed impact with interstellar dust. The materials sourced for these vehicles must be obtained responsibly, avoiding terrestrial conflicts and environmental degradation, because a ship built for a noble journey should not begin its life by causing harm. This extends to the sheer energy consumption of an interstellar drive. Is it ethical to dedicate the planetary resources required to power a single mission, resources that could otherwise address pressing needs here at home? The answers are not simple, but they are inescapable. These moral calculations must be woven into the design from the very first sketch, long before any prototype is ever printed. Yet for an ethically sound design to ever leave the drawing board, it must also answer to the relentless logic of economics, finding a way to balance our highest ideals with the practical demands of cost and feasibility. A painter standing before a canvas faces a choice between rare, costly pigments and common, affordable paints. Both can create art, but only one path leads to a masterpiece the world can actually afford to own. This is the precise dilemma at the heart of interstellar propulsion, where the most breathtaking artistic vision must eventually answer to the unyielding logic of economics. The development of these systems is a marathon, not a sprint, requiring decades of sustained investment before a single ship ever leaves the dock. Research grants from government agencies form the initial lifeblood, but these funds are often limited and subject to political shifts. Private investment from visionaries can inject tremendous momentum, yet it demands a credible path to a return, a nearly impossible promise for technologies that may not see practical use for a century. This financial tightrope forces a new kind of creativity upon artists and engineers alike. They must now design systems that are not only theoretically brilliant and visually compelling, but also cost-effective to manufacture, assemble, and operate. The goal is to achieve radical innovation without resorting to astronomically expensive, one-off solutions. Entrepreneurs like Elon Musk have fundamentally shifted this conversation by relentlessly focusing on cost reduction. He has famously stated that making humanity a multi-planetary species requires bringing the price of reaching orbit down by orders of magnitude, treating astronomical launch costs not as a given, but as a problem to be solved through engineering and manufacturing efficiency. This philosophy trickles down to the very components of a propulsion system. Engineers increasingly look to commercial off-the-shelf, or COTS, components. Instead of designing a custom, multi-million-dollar computer chip for a deep space probe, they might adapt radiation-hardened versions of processors used in consumer electronics, achieving reliability at a fraction of the development cost. Scalable design principles are equally critical. A successful ion thruster, for instance, should not be a unique masterpiece. Its design should be modular, allowing it to be scaled up for a large cargo vessel or scaled down for a small satellite, spreading its research and development costs across a whole family of engines. This is where public-private partnerships create powerful synergies. Programs like NAS, Small Business Innovation Research, or SBIR, initiative provide targeted grants to small companies working on high-risk, high-reward propulsion technologies. A tiny startup with a revolutionary design for a plasma thruster can receive the seed funding to build a prototype, leveraging public investment to de-risk the technology for future private capital. This collaborative model builds a bridge between the boundless imagination of the artist and the pragmatic balance sheet of the investor. So we are left with a reflective, almost philosophical question. Can the most beautiful, elegant design for a starship ever truly be the most affordable one? Or is there an inherent tension where budget constraints inevitably sand away the most daring and beautiful edges of a concept? The answer may lie in redefining our idea of beauty itself. Perhaps the most beautiful design is not the one with the most dramatic curves, but the one that achieves its majestic goal with such elegant efficiency that it becomes financially possible to build. This is the ultimate artistry, the genius of a design that balances the dream of the stars with the practicalities of the ledger. The interior of a long-duration crew capsule feels nothing like a sterile machine. Its walls curve in soft, organic forms bathed in the gentle glow of a simulated dawn. This is not an aesthetic whim, it is a psychological necessity. Every contour and hue is a deliberate defense against the profound stresses of isolation and confinement millions of miles from home. A new discipline, aerospace psychology, has emerged to study this exact phenomenon, focusing on how design directly shapes crew morale, cognitive function, and ultimately, mission success. Psychologists working with astronauts on the International Space Station have gathered crucial data, revealing that even small design improvements can have dramatic effects. They advocate for incorporating natural elements wherever possible. A living quarters wall might display a slow-motion video of a forest stream, or use textured panels that mimic the feel of wood grain. This is not mere decoration, it is a vital tether to the world the crew has left behind, a tool to combat the sensory deprivation of the metal box they inhabit. Aesthetic harmony is equally critical. Cluttered, chaotic control panels increase cognitive load and the risk of error during high-stress maneuvers. The solution is a design philosophy that prioritizes intuitive layouts, where the most frequently used controls fall naturally to hand and critical status displays are instantly legible without conscious thought. Personal space, even just a small, enclosed nook an astronaut can call their own, becomes a sacred retreat for psychological recovery. We are now seeing these principles applied in remarkable ways. For ships that must be windowless for structural integrity, high-resolution screens can act as virtual windows, offering a real-time, panoramic view of the cosmos outside. This connection to the external environment is crucial for maintaining a sense of place and purpose. Control interfaces are beginning to incorporate subtle biometric feedback, changing color or layout if they detect a rise in the operator's stress level, prompting a moment of conscious recalibration. Even artistic installations serve a function, with dynamic light sculptures or generative music systems designed to break the crushing monotony of a years-long journey. The SpaceX Crew Dragon capsule is a tangible step in this direction. Its minimalist, user-friendly touchscreen interfaces and clean, uncluttered interior represent a significant shift from the dense, switch-covered panels of the past. This is psychologically informed engineering in action, recognizing that the human brain is as important a system as the propulsion drive. So as you envision these future ships, ask yourself not just how they will travel, but how they will feel to the humans inside. How can a hallway, a chair, or a view screen be designed to support a mind thriving at the edge of human experience? A starship should sail through the cosmos like a leaf on the solar wind, leaving no scar on the void it crosses. This vision of deep space sustainability is reshaping propulsion artistry, demanding that our grandest vehicles are not only powerful but also gentle on the universe. The principle is simple yet profound. We must design systems that minimize resource depletion and avoid creating permanent debris, even in the seemingly infinite expanse between stars. Artists translating this ethos into visuals often depict ships with vast, shimmering solar sails or elegantly contained fusion reactors that fuse hydrogen, the universe's most abundant element. Their renderings are not just beautiful, they are manifestos for a new kind of exploration, one that carries our growing ecological consciousness from Earth into the galaxy. Sustainability advocates within the aerospace industry are vocal about this responsibility. One lead designer at the European Space Agency remarked that our greatest challenge is not reaching the stars, but ensuring we do so without exporting our terrestrial problems of waste and short-term thinking. This philosophy is codified in efforts like the ESA's Clean Space Initiative, a comprehensive program dedicated to reducing the environmental impact of space missions from construction to end-of-life disposal. It pushes for propulsion systems that leave no spent boosters in orbit and spacecraft that can deorbit themselves safely, burning up completely or returning to a designated graveyard orbit. This responsibility extends to a rigorous life cycle assessment for every component. Engineers now analyze the total environmental cost of a thruster, from the energy and water used in mining its rare earth metals to the pollution generated by its manufacturing, and ultimately, the feasibility of its safe disposal or reuse. The goal is to design for disassembly from the very beginning. Imagine a magnetic plasma nozzle constructed in modular segments, each one easily unbolted and replaced, with its valuable materials separated and fed back into the production cycle for the next generation of engines. This circular economy mindset is crucial for missions that could last centuries. Biological systems become vital partners in this endeavor, transforming a Starship from a mere vehicle into a self-sustaining ecosystem. Artists' concepts increasingly show vessels woven with photosynthetic bioreactors, where genetically engineered algae or bacteria not only recycle carbon dioxide into breathable oxygen, but also form the base layer of a closed-loop food and water purification system. These living engines would work in silent harmony with the propulsion drive, ensuring the ship's life support is as renewable as its method of travel. So we are left with a haunting question as we prepare to step beyond our cradle. How do we ensure that our greatest adventure does not become just another chapter in the story of our consumption? The artistry of our propulsion systems may hold the answer, reflecting a future where humanity learns to thrive among the stars without harming them. A dozen minds are crowded around a single digital whiteboard, their voices a chorus of conflicting expertise. An artist points to a sweeping curve on a warp nacelle, arguing for its visual drama, while a materials physicist immediately counters, explaining how that same curve would create a catastrophic stress concentration under subspace tension. A philosopher quietly interjects, asking if the very shape of the drive implies a violent passage through space that we might want to ethically reconsider. This intense, focused brainstorming session is known as a design charrette, and it is the crucible where interstellar vehicles are forged. In these rooms, the solitary genius myth dies, replaced by the messy, brilliant reality of multidisciplinary teamwork. No single person can hold all the knowledge required to design a starship. The artist cannot know the quantum limitations of a containment field, and the physicist may not grasp the psychological impact of a claustrophobic corridor on a decades-long journey. Their collaboration is not a linear handoff from artist to engineer to builder. It is an integrated, agile process, a continuous loop of creation, critique, and refinement that happens in near real time. Project managers at initiatives like Breakthrough Starshot describe their role as conducting an orchestra of experts, ensuring the physicists are not playing a waltz while the engineers are trying to keep up with a frenetic jazz solo. They use sophisticated digital platforms that act as a shared nervous system for the project. A thermal engineer in Tokyo can leave a comment on a 3D model, and a structural designer in California will see it highlighted in their augmented reality headset moments later, allowing them to adjust a support beam before the design is even finalized. This requires profound tools for conflict resolution. Creative disagreements are not suppressed, they are harnessed. When an artist and an engineer clash over a design element, the conflict is framed as a problem to be solved, not a battle to be won. The question becomes, how can we achieve the aesthetic vision without breaking the laws of physics? This often leads to the most innovative solutions, where a constraint becomes the mother of invention. Into this technical fray steps the user experience, or UX designer, a role once reserved for smartphone apps but now critical for Starship design. They represent the human in the loop, constantly asking how a crew member will interact with this system during a moment of panic or extreme fatigue. They work to integrate intuitive feedback into control panels, perhaps using haptic vibrations or color shifts to communicate system status without overloading the crew's conscious attention. Fostering an inclusive culture is not a sidebar, it is a strategic necessity for innovation. The most groundbreaking ideas often come from the intersections between fields, from the biologist who suggests a self-healing polymer based on coral growth, or the ethicist who questions the long-term societal impact of a propulsion technology that only the ultra-wealthy can access. We need only look to the James Webb Space Telescope for a monumental example. Its development was not the work of a single agency, but a vast global collaboration spanning decades, involving thousands of scientists, engineers, and technicians. They navigated immense technical hurdles and budget crises, their success hinging on a shared, documented language that allowed knowledge to be passed seamlessly from one team to the next over many years. This highlights the final, crucial layer of the process: documentation. The collective intelligence generated in these charrettes is too valuable to lose. Every decision, every rejected concept, and every hard-won compromise must be captured, creating a living memory for the project. This documented journey itself becomes a blueprint, not just for building a ship, but for the very process of collaboration, ensuring that the lessons learned by one generation can be inherited by the next. How do we preserve not only the final blueprint, but the rich human conversation that brought it into being? An AI curator floats in a zero-G studio, its consciousness a river of live astrophysics data. It watches gravitational wave detections from distant neutron star mergers and real-time maps of interstellar magnetic fields, then sketches not with a pencil but with structured light. A holographic propulsion system blooms in the center of the room, its form fluidly adapting to each new data stream. This is not a far-off dream. It is the next logical step in our creative evolution, where artificial intelligence becomes a co-creator in the artistry of interstellar travel. The acceleration is breathtaking. Futurist Ray Kurzweil has long predicted that technological change is exponential, not linear, and we are now approaching the steep part of the curve for space travel. What does this mean for our designs? It means the very tools we use to imagine are transforming. Quantum computing will soon allow us to simulate propulsion systems in their entirety, modeling not just fluid dynamics but the quantum vacuum fluctuations a ship might tap into for thrust. These are environments so complex that today's supercomputers can only offer approximations. With quantum simulation, an artist could tweak the geometry of a theoretical drive and instantly see how that change ripples through the fabric of spacetime itself, watching the stresses on the hull resolve in real time. This expanded palette extends to the materials themselves. Nanotechnology promises engines that assemble themselves, where programmable nanites follow a digital blueprint to construct a thruster from the molecular level up, creating structures with perfect atomic alignment and zero waste. Imagine a magnetic sail that can heal a micrometeoroid puncture by directing a swarm of these tiny builders to the site, the repair happening automatically while the ship is still underway. Even biology is becoming a partner in propulsion. Research into organic-inorganic hybrids explores how we might grow certain engine components, using modified biological processes to create super-strong, self-regulating materials. A photosynthetic coating on a hull could theoretically convert stellar radiation directly into electrical power, while engineered fungi could be used to recycle waste into usable propellant, blurring the line between a machine and a living organism. This fusion of disciplines will unlock forms previously confined to pure imagination. Photonic propulsion, which uses the literal pressure of light for thrust, is a stunning example of this convergence. Current research at institutions like the Breakthrough Starship Initiative is already testing the limits of this idea, envisioning tiny probes pushed by powerful lasers. The artistic challenge then becomes, what is the form of a ship that rides a beam of light? Its design would be a direct reflection of that pure energy, perhaps a vast, impossibly thin sail that looks more like a soap bubble than a vessel, shimmering with the full spectrum of a star's output. This leads to a future of deeply personalized spacecraft. An AI design assistant, trained on your preferences and physiological data, could generate a unique hull form optimized for your comfort and the mission profile. You might simply describe the feeling you want the ship to evoke, serene and meditative or dynamic and aggressive, and the system would produce 100 variations, each a valid engineering solution and a unique work of art. But this autonomy forces a difficult ethical question. When an AI can design a better, safer, more efficient starship than any human team, do we surrender our creative authority? Where does human intention end and machine optimization begin in the blueprint for a vessel that represents our entire species? The responsibility remains ours to guide these tools, to ensure that the values of beauty, ethics, and wonder are encoded into their very algorithms. The future of propulsion artistry is not about replacing the human spirit, but about giving it new mediums in which to soar. As these tools redefine what is possible to build, they will also fundamentally redefine our relationship with the cosmos, transforming us from observers of the great dark into conscious shapers of its infinite possibilities. A young woman named Anya first glimpsed her future not in a textbook, but while sketching a nebula during an astronomy lecture. Her passion for cosmic art led her to a unique university program blending industrial design with foundational aerospace engineering. Today, she collaborates with a research lab visualizing next-generation propulsion concepts, her digital art giving form to theories that once lived only in equations. Her journey reveals that the path to designing interstellar vehicles is no longer a single, narrow road, but a sprawling network of intersecting disciplines. For those drawn to this field, the first step is recognizing that your unique combination of interests is not a distraction, but your greatest asset. The educational routes are wonderfully varied. A degree in industrial design teaches you how to shape objects that are both beautiful and functional, while aerospace engineering provides the deep technical knowledge of propulsion physics and materials science. Astrophysics offers a window into the fundamental laws of the cosmos you are designing for, and even science communication is a vital pathway, as the ability to explain complex ideas can inspire the public and secure the funding to make these ships real. The key is interdisciplinary learning. An art student benefits enormously from a basic physics course, understanding why a hull must have a certain shape to withstand atmospheric pressure. An engineering student taking a life drawing class hones their observational skills and learns to think about form in a more intuitive way. Professionals at NASA, advanced concepts team, and experimental groups like the Sci-Fi Lab consistently emphasize this blend. They are not just looking for brilliant engineers or talented artists, they are seeking hybrid thinkers who can translate between these different languages. One lead designer at a private aerospace firm noted that their most valuable hires are those who are comfortable being the bridge in a conversation between a quantum physicist and a materials sculptor. Building a compelling portfolio is your most powerful tool. Fill it with speculative designs, your own artistic interpretations of an antimatter rocket or a gravitational lens ship. Treat each piece as a solved problem, explaining not just what the ship looks like, but why you made each design choice based on hypothetical physics. This demonstrates your unique ability to think creatively within constraints, actively network at conferences, both scientific and artistic, as the most groundbreaking collaborations often spark in the hallways between formal presentations. And never stop learning. Online courses in everything from plasma dynamics to advanced 3D modeling software allow you to continuously expand your skill set from anywhere in the world. Consider the SpaceX internship program, which famously seeks out candidates from wildly diverse academic backgrounds. A philosophy major might be hired for their expertise in ethical reasoning applied to autonomous spacecraft systems, while a graphic designer might be tasked with creating intuitive control panel interfaces. This reflects a fundamental truth: the Starship of the future will be built by a crew of specialists, but it will be conceived by generalists. So what unique talent do you bring to the drafting table? Is it your eye for color and composition, your relentless curiosity for how things work, or your gift for weaving a compelling narrative? The next great propulsion artist may not be the one with the highest test scores, but the one who can best connect the dots between a blackboard equation and the human dream of sailing on the solar wind. Miguel Alcubierre published his foundational paper in 1994, a dense set of mathematical proofs that offered a tantalizing possibility. A spacecraft could ride a wave of compressed spacetime, moving faster than light without ever breaking the universal speed limit locally. The equations were elegant, but they were just symbols on a page until artists gave them a face. Early sketches began to emerge, depicting a ship cradled within a flat region of spacetime, a warp bubble, while the cosmos ahead was crushed into a deep blue and stretched into a blinding red behind it. This visual translation was not just an aid, it was a catalyst, turning an abstract tensor calculation into a shared dream that physicists and engineers could collectively chase. The key components of the drive are as bizarre as they are beautiful. The warp bubble itself is a region of normal space, a safe pocket for the ship and its crew, surrounded by a ring of exotic matter. This ring generates the negative energy density required to twist spacetime into the necessary expansion and contraction. Artists illustrating this concept faced a unique challenge. How do you draw something that, by its nature, warps the very light used to see it? Their solution was to visualize the distortion itself. They depicted the stars around the ship not as points of light, but as long, streaking lines, a direct illustration of the immense gravitational lensing effect the bubble would produce. This collaboration between theoretical physicists and concept artists is a continuous dialogue. The physicist provides the rules of the game, the mathematical constraints, and the artist plays within that sandbox to create something both believable and inspiring. Dr. Harold Sonny White, a prominent researcher in the field, has spoken about this synergy, noting that while the energy requirements initially seemed astronomical, refinements in the geometry of the warp bubble have brought them down to more conceivable levels. His team's experimental work involves trying to create microscopic warp effects in the lab, using sophisticated interferometers to detect spacetime distortions a fraction of the width of a human hair. These experiments, in turn, give artists new data points, leading to renderings that are less speculative and more grounded in emerging science. The material challenges for constructing such a bubble are staggering. What substance could possibly maintain the integrity of a spacetime distortion? Artists often visualize the exotic matter ring as a shimmering, ethereal torus, a ring of glowing energy that seems to vibrate with latent power. This artistic choice hints at the theoretical need for a material with negative mass, a substance that currently exists only in mathematical theory and certain quantum experiments. The energy source required to sustain the warp field is another focal point for designers. Early concepts simply showed the ring glowing, but as the science evolved, so did the art. Many modern interpretations integrate the warp ring with a massive fusion reactor or even a matter-antimatter annihilation core, illustrating the vessel's heart as a contained star, feeding energy into the space-time manipulating structure. Scale is a constant consideration. An Alcubierre drive capable of transporting a human crew would need to be immense. The ship itself might be relatively small, nestled at the center, but the warp ring surrounding it would have to be colossal, perhaps dozens of kilometers in diameter. This necessity has led to stunning artistic renditions, from the scientifically informed diagrams in NASA at technical publications to the iconic, sleek, nacelled starships of Star Trek, which popularized the very idea of warp travel for generations. The Enterprise, with its distinct engineering hull and glowing warp coils, is a perfect example of artistic license serving a functional narrative, making a deeply complex idea feel intuitive and thrilling. This single case study illuminates the path for all other theoretical systems. The process for an Alcubierre drive, from equation to sketch to lab experiment, provides a blueprint for how we might one day approach the visualization and engineering of a traversable wormhole or a quantum vacuum thruster. Each begins as a set of immutable laws, awaiting the artist's hand to give it a form, and the engineers resolve to ask, how can we build it? A gossamer sail thinner than a soap bubble billows in the void, its vast surface shimmering with the silent, relentless pressure of light itself. This poetic vision of sailing on sunbeams has captivated dreamers for centuries, but its journey from a scientist's daydream to a tangible spacecraft reveals the profound artistry behind interstellar propulsion. The story begins not in a modern lab, but in the 17th century with astronomer Johannes Kepler. Observing the tails of comets being pushed by what he thought was a solar breeze, he wrote a letter to Galileo, musing that one day vessels and sails might be fashioned to ride upon that very ethereal force. He saw the connection between the heavens and the sea, a metaphor that would inspire generations. Centuries later, that metaphor was given mathematical form, and the modern light sail was born. Artists tasked with depicting this concept face a unique challenge, capturing the ethereal beauty of a structure that is almost nothing, while grounding it in the harsh realities of physics. Their renderings show vast, silvered sheets, often crisscrossed with a delicate web of nanowires, looking less like a rigid spacecraft and more like a celestial jellyfish drifting through the black. This aesthetic is not just for show, it directly communicates the sail's function, a structure where mass is the enemy and surface area is the engine. Scientists on projects like Breakthrough Starship explain that the design choices are dictated by brutal efficiency. The sail must be perfectly reflective to maximize momentum transfer from photons, leading to the use of advanced metamaterials engineered at the atomic level. Its shape is often a perfect square or a disc, not for visual appeal, but to ensure an even distribution of the immense laser light that would push it, preventing a catastrophic tumble. Perhaps the most intricate artistry lies in the sail's deployment mechanism. An interstellar light sail must be launched in a tiny, folded package, a piece of cosmic origami that unfurls flawlessly millions of miles from Earth. Artists visualize this transformation as a silent, balletic bloom in the deep space, a moment where engineering achieves a kind of mechanical poetry. We have already witnessed this poetry in action. The Planetary Society's Light Sail 2 mission, a citizen-funded spacecraft no larger than a loaf of bread, successfully raised its orbit around Earth using only the pressure of sunlight on its 32 square meter miler sail. The photographs it beamed back were breathtaking, showing our planet reflected in a shimmering silver rectangle, a working proof that we can indeed sail on light. Yet these beautiful, delicate structures must endure a gauntlet of horrors, from the piercing shrapnel of micrometeoroids to the relentless degradation of atomic oxygen and ultraviolet radiation. How does something so exquisitely fragile survive a 20-year journey to another star? The answer is woven into its very fabric, in the self-healing capacities of its nanomaterials and the redundancy of its network design. This forces us to confront a deeper question. Is the most beautiful design for a starship the one that appears most powerful, or the one that, like a dandelion seed, achieves the impossible through graceful, resilient simplicity? A designer types 3 words into a console: elegant, efficient, and interstellar. In less than a second, a cascade of 100 unique propulsion systems floods the screen, each a breathtaking synthesis of mathematical law and aesthetic vision. This is the new creative partnership, where artificial intelligence acts not as a mere tool, but as a co-creator in the artistry of interstellar travel. These machine learning algorithms are trained on a vast and eclectic diet, consuming everything from decades of plasma physics research and materials science papers to the complete works of visionary artists like Sid Mead. They learn the hidden patterns that connect a beautiful curve to a stable energy flow and a sweeping hull to effective heat dissipation. By processing this immense library of human knowledge, the AI can propose radical design configurations that a human mind, bound by cognitive biases and traditional thinking, might never conceive. It operates in a space of pure possibility, blending efficiency with a startling new aesthetic appeal. An AI researcher from a major creative tech firm describes this process as a dialogue with an alien intelligence that has perfect recall. We are not asking the machine to be creative in the human sense, she explains, but to perform a superhuman feat of combinatorial optimization. It can test 1 billion subtle variations on a magnetic nozzle design, for instance, and present the 5 that are both 99% structurally optimal and visually resonate with the specified artistic style, whether that is biomimetic or starkly minimalist. The engine behind much of this generative art is something called a Generative Adversarial Network, or GAN. This system pits 2 neural networks against each other, one generating new images and the other critiquing them for realism based on its training data. The result is a rapid evolution of concepts, pushing through countless failures to arrive at designs that are not only novel but also physically plausible. These AI-generated renderings are then fed directly into simulation software, creating a closed loop of creation and validation. The AI can take its own concept for a warp ring and immediately subject it to a simulated stress test, watching how the structure handles the theoretical forces of compressed spacetime. It learns from each simulation, refining its next batch of designs in an accelerated digital evolution. We see a powerful, real-world precedent in NASA, a use of AI to design specialized spacecraft components. Engineers provided the AI with basic goals: maximize strength while minimizing mass, and the resulting structures were bizarre, organic, and lattice-like forms that looked grown rather than machined. Yet they were significantly lighter and stronger than any human-designed equivalent, proving that AI can find a deeper, more efficient geometry hidden within the problem's constraints. This newfound capability forces a necessary ethical conversation about authorship and intention. When a stunning Starship design emerges from an algorithm, who is the true artist? The programmer who coded the AI, the designer who set the parameters, or the AI itself? The creative industry is grappling with this, seeking a balance where the machine's computational power amplifies human intuition rather than replacing it. The goal is a symbiotic relationship where the human provides the dream, the ethical framework, and the cultural context, and the AI provides the near-infinite palette of forms to realize it. So we must ask, as AI begins to dream alongside us, what becomes the primary role of the human artist? Is it to master the machine or to curate its visions, guiding our collective imagination toward futures that are not only possible but also profoundly meaningful? A polished stainless steel rocket gleaming under the sun does more than just reflect light. It captures the collective imagination of an entire planet. The visual power of a design like the SpaceX Starship is not an accidental byproduct. It is a core feature of its engineering, calculated to generate public excitement and transform the abstract concept of space travel into a tangible, imminent reality. This phenomenon is known as visioneering, the practice of using compelling artistic and technological visions to build the cultural and political momentum necessary for monumental projects. When people can see a sleek, powerful vehicle, they are far more likely to believe in its mission and support the decades of work and billions in funding required to make it fly. Science communicator Neil deGrasse Tyson often emphasizes that the human brain is wired for visuals, not equations. A single, stunning rendering of a spacecraft skimming the clouds of Jupiter can do more to explain the principles of atmospheric entry and gravitational assist than a semester of physics lectures. This relatable imagery builds a critical bridge, allowing complex science to bypass intellectual barriers and connect directly with our sense of wonder. Media representations are the primary engine for this connection. Documentaries now use photorealistic computer-generated imagery to take viewers on journeys through the rings of Saturn, while video games allow millions to virtually pilot ships with intricate, fictional propulsion systems, teaching intuitive lessons about orbital mechanics and thrust. Museums have evolved from static displays to immersive experiences, where you can stand beneath a full-scale model of a Mars lander or use virtual reality to guide a simulated ion thruster through an asteroid field. These are not passive exhibits, they are carefully crafted artistic installations designed to make you feel the scale and possibility of interstellar travel. The Apollo program understood this power profoundly. Before a single Saturn V rocket ever left the pad, artists like Robert McCall and Chesley Bonestell were hired to paint the missions. Their breathtaking works visualized the lunar landings, the views from orbit, and the stark beauty of the moon's surface, creating a vivid and emotionally resonant preview for the entire world. These paintings were not just promotional, they were a form of visual planning, helping engineers and the public alike to see the future. Today, this tradition continues through crowd-funded space art projects, where communities collectively support artists to visualize ambitious concepts, from O'Neill cylinders to Dyson spheres, proving there is a massive public appetite for visions of a hopeful, expansive future. Yet this artistic power carries a profound responsibility. The excitement generated by a beautiful design must be anchored in scientific plausibility, or it risks creating a backlash of disillusionment. How do we balance the need to inspire with the duty to be accurate? The most effective science communication uses artistry not to deceive, but to illuminate, turning the real, staggering truths of the cosmos into a narrative that feels as thrilling as any fiction, ensuring that public enthusiasm is built on a foundation of genuine understanding. A propulsion system's most beautiful line might be the one you never see, the graceful curve of a fuel line routed to avoid a critical pressure vessel. In a brightly lit design studio, a team debates the placement of a vital emergency shutoff valve. The regulations are clear. It must be accessible within 3 seconds by a crew member wearing a bulky pressure suit. Yet the artist's vision calls for a clean, unbroken hull surface. This is the daily reality of regulatory artistry, where safety protocols are not constraints to work around, but a foundational design language. Bodies like the Federal Aviation Administration Office of Commercial Space Transportation and the United Nations Office for Outer Space Affairs establish these international standards, creating a framework that ensures every vehicle is not just a marvel of engineering, but a sanctuary for its crew. The challenge is to weave these necessities so seamlessly into the ship's form that they become invisible until the moment they are desperately needed. A senior safety engineer at a major aerospace firm describes this as the ultimate design puzzle. "We are not just bolting on safety features," she explains. "We are asking how a radiation shield can also be a structural member, or how the geometry of a warp coil housing can naturally channel coolant in the event of a primary system failure." The goal is to make the safest path for energy, heat, and human movement also the most elegant and intuitive one. This philosophy manifests in subtle, brilliant details. Propellant lines are color-coded not with garish paint, but with subtle anodized hues or textured wraps, allowing a technician to identify a hypergolic fuel line from a liquid oxygen line at a glance, even in low light. Control interfaces for crisis management are designed with a layered simplicity. During normal operation, the console is a model of minimalist calm. But if a pressure leak is detected, the system does not just sound an alarm. It visually simplifies the display, highlighting only the essential controls for sealing bulkheads and stabilizing the ship, guiding the crew's hands with an unspoken, artistic clarity. The artistry in fail-safe mechanisms is particularly profound. Consider the launch abort system on the SpaceX Crew Dragon. Its sleek exterior gives no hint of the powerful Super Draco engines hidden just beneath the surface, ready to pull the entire capsule away from a failing rocket in a heartbeat. The system's cover is not a clumsy hatch, but an integral part of the vehicle's smooth, modern aesthetic, a piece that jettisons away with explosive elegance to reveal the raw safety mechanism underneath. This integration raises a critical question: how can the simple, thoughtful placement of a handle or the intuitive layout of a screen become the difference between life and death in the chaotic, high-stakes environment of space? The answer lies in recognizing that safety is not a checklist, but a continuous, creative discipline. It is the art of foreseeing the unforeseeable and designing a vessel that responds not with complexity, but with graceful, resilient intelligence. A future archaeologist, brushing dust from a crystalline data slab, gazes upon our century's first fumbling sketches of starships. To them, these early concepts of warp drives and light sails will appear with the same poignant mix of ambition and nascent understanding that we see in Leonardo da Vinci's flying machines. This is the true legacy of interstellar design, a conversation we are starting today that may not be finished for 1,000 years. Our current artistry is not merely for ourselves, it is the foundational bedrock, the primordial sketchbook, upon which generations of engineers and artists will build. We are creating the visual and intellectual vocabulary for humanity's cosmic future. This makes the documentation of our creative process not an administrative task, but a profound ethical duty. Every discarded sketch, every simulation log, and every record of a heated design debate is a crucial part of the historical record. It shows the winding path of progress, the dead ends that taught us as much as the breakthroughs, preserving the collective intelligence of our era for the pioneers who will one day stand on our shoulders. Historians of science often note that innovation is rarely a single eureka, a moment, but a slow accretion of ideas across centuries. The principles of the rocket were understood long before the technology existed to build one, and the artistic vision of a spacefaring civilization has been simmering in our culture for generations. Our work today is the vital link in that chain, transforming ancient dreams into structured, testable hypotheses. This legacy is now entrusted to digital archives, vast libraries of light that preserve every iteration of a propulsion concept. Unlike paper, which crumbles, these archives can hold not just the final blueprint, but the entire creative journey, the video of a design charrette, the holographic model of a prototype, and the physicist's notes scribbled in the margins of a sketch. This living record ensures that the reasoning behind every curve and coil is never lost, allowing future minds to understand not just what we built, but why we built it that way. We have a powerful precedent for this long-term thinking in the Voyager Golden Record. That artifact was not a technical schematic, but a piece of artistic propulsion in its own right, a capsule of our culture launched into the void on a journey of thousands of years. It was an act of profound hope, a message meant for a future discoverer we will never meet. Our Starship designs are a similar message, but for our own descendants. They are a blueprint of our hopes and our current understanding of the universe's laws. This legacy carries an immense ethical weight, forcing us to consider the long-term impacts of the technologies we are visualizing. Are we designing vessels that promote exploration without exploitation, that prioritize sustainability and respect for any life we might encounter? The cultural and philosophical values we encode into these early designs will ripple outward, influencing the very nature of interstellar society for millennia to come. The artists and engineers of the 30th century will look back at our work, not to copy it, but to be inspired by it. They will see our ambition, our initial grappling with forces we barely comprehend, and our unwavering belief that humanity has a destiny among the stars. Your own perspective, your unique way of seeing the world, is a part of this unfolding story. Whether you are sketching ideas in a notebook, sharing a rendering online, or simply gazing at the stars with wonder, you are contributing to the legacy. What part of our interstellar dream will you help to draw? That single pencil stroke has now grown into a vessel ready to cross the light years. Our journey from the quiet solitude of the artist's studio to the roar of the launchpad reveals a profound truth. The line between a creative sketch and a functioning starship was never a boundary at all. It was a collaboration, a continuous loop where imagination inspires physics and physics, in turn, refines imagination. This seamless fusion of disciplines is what transforms the impossible into the inevitable. The key takeaway is not just a set of technical steps, but a new way of thinking. It demands that we champion creative vision without fear of the constraints, that we build bridges between the artist's studio and the engineering lab, and that we anchor every ambitious design in a deep ethical consideration for the universe we are about to enter. This process does more than advance our technology. It elevates our culture, filling our collective imagination with new possibilities and reminding us that exploration is the most human of all endeavors. The visionary author Arthur C. Clarke once observed that the planets are not distant points of light but worlds, and that the Earth is only a cradle, and one cannot live in a cradle forever. This is the future we are sketching into existence right now, a future beyond the cradle. Your own perspective is a vital part of this ongoing story. Whether you pick up a pencil to draft your own starship, share a rendering that captures your wonder, or simply choose to support the innovators pushing these boundaries, you are contributing to the legacy. We would love to see your visions, so if you have a concept for an interstellar vehicle, share a sketch or describe it in the comments below. For more deep dives into the technology shaping our future, make sure to subscribe. Together, we are not just watching the future arrive, we are drawing its